Good morning, geometers. We're going to start a new chapter today, and we're down to the last couple of lessons for the year, so it kind of makes us sad, doesn't it? Alright, today we're going to start in on chapter 12. Chapter 12's focus is on the shape of circles. Now, the first thing we want to talk about is something called a tangent line. In section 12.1, we're going to talk about something called tangents and circles, or tangent lines and circles. Now, the first thing we want to do is define what a tangent line is. A tangent line is a line that intersects a circle at exactly one point. Now, it's a line, and therefore we know that lines go on forever in both directions, whereas another type of line that we're going to be interested in circles is something called a secant line. A secant line is a line, but at this time a secant line will intersect a circle at 2 points. Now, in my drawing here, I have both a tangent line and a secant line. Notice how the tangent line meets at only this one red point on the circle, whereas the secant line will touch at 2 points. Now, for tangent lines, the point where the line and the circle intersect is called your point of tangency. Now, again, we're going to leave secant lines for now, and we're just going to focus on the tangent line and some important theorems that we know about them. Now, the first theorem that we have is what I like to call the radius tangent theorem. And it basically says that if you have a radius that intersects a tangent, then the radius and the tangent will always be perpendicular. So in this picture, I have radius OA, and I have tangent line AB. Well, they will always be, if they intersect, then they'll always make a right angle. They'll always be perpendicular, so I can assume that OA is perpendicular to AB. Now, because of that, we can use our old friend Pythag to help us solve for missing lengths. Let's take a look at some examples. In this example A, I'm asked to solve for this length x that's outside the circle. Okay? Well, let's see here. I don't know anything right now. I've drawn a triangle in here, but off of what we just learned, since this segment right here is a radius and I have got a tangent, I can assume that's a right angle. Well, because of that, I can use Pythagorean theorem to solve. Now, there's a couple ways you could solve for x here, but I'm going to go ahead and do it the algebraic way. I'm going to say that I know that one of the legs of the right triangle is 15, the other leg is 8, and I'm only looking for part of the hypotenuse, right? Well, don't forget that if I have two radii in a circle, I know that all radii in a circle are congruent. So if this length is 8, this other length right here must also be 8. So I could set up the Pythagorean theorem that says a squared plus b squared equals the hypotenuse squared. And now I've just created an algebra problem. So solving, I would get 64 plus 225 equals, multiplying this out, I would get x squared plus 16x plus 64, right? From here, I know I need, because it's a quadratic, I need to make one side 0. So I'm going to subtract the 64. Actually, let's add this together. I get 289 equals x squared plus 16x plus 64. Subtracting the 289 across, I get 0 equals x squared plus 16x minus 225. And then factoring, I say, well, it multiplies to give me negative 225. That adds or subtracts to give me 16. Well, I believe it would be positive 25 and negative 9. So those would be the two factors. Setting each factor equal to 0, I would get x equals negative 25 and x equals 9. But again, because I'm looking for a length, it can't be x equals negative 25, so the only answer would be 9. Now, I will say there's a much shorter way of doing this problem that I would suggest doing. I want you to think about how you could do it in a quicker fashion. Let's do example B here. In example B, call this guy B. Again, I'm looking for x, but in this case, x is my radius. Now, 8 represents, again, this outer segment right here. So how can I solve for x? Well, again, because all radii are congruent, I know that if this length is x, this radius has to also have a length of x. So setting up my Pythagorean theorem, it would, oh wait, because my radius and my tangent intersect, they make a right angle. And I can set up the equation x squared plus 12 squared equals x plus 8 squared. Simplifying, I get x squared plus 144 equals, now multiplying this side out, I would get x squared plus 16x again plus 64. Now again, because it's quadratic, the x squared makes it quadratic, I need to move everything to one side. So I'm going to subtract the x squared across, subtract the 144 across. I get 0 equals, well, lo and behold, the x squareds cancel, so I'm left with, subtracting the 144, I get x squared canceling, so I get 16x minus 80 equals 0. So now I can just solve this equation as a linear equation. I can just add the 80 across, so I get 80 equals 16x. Dividing both sides by 16, I would get x equals 5. So the length of that radius must be 5. Alright? Okay, and that's a big idea. Anytime you have a radius and a tangent intersecting, they always form a right angle. In other words, they're always going to be perpendicular. Okay, the next idea. This next idea, I call this the congruent tangents theorem. Again, this is just my own name. Here's what this theorem says. It says, if two tangents intersect outside a circle, then the distances from the point of intersection to the points of tangency will be equal. So I've got two tangents, tangent AB and tangent AC. Since these two tangents intersect at this point A, I know the distance from A to B will be equal to the distance from A to C. Right? I can always assume that. Now, using that idea, I could do problems that look like this. I'm going to find the perimeter of the polygon that circumscribes the circle. Now again, when something circumscribes something, that means circumscribing means it's outside the shape, and again you have these tangents. The shape is only touching the outside shape at one point. Okay, now using the theorem we said above, I know that since I have two tangents that are intersecting at this point, if this distance from here to here is 9, then the distance from here to here must also be 9. Likewise, if the distance from here to here is 7, then this distance has to be 7. If this length is 8, then that length is 8. And lastly, if this is 2, then that also must be 2. Now to find the perimeter, again, the perimeter is just the lengths of all the sides added together. So I'm going to have a perimeter of, okay, let's see, I've got 10 plus 11 plus 16 plus 15, right? So here's my 10, here's my 11, here's my 16, and here's my 15. So summing these together, I would get a length of 52. So that would be your perimeter. Alrighty folks, that's it for this section. We'll see you later.